Growing up, my friends used to always ask me if my dad was in the military because my family moved around so much. And I tell them it's kind of like that. He works for a big oil company, but we did move around a lot. I was born in New Orleans, then we moved to Houston, and then it was San Francisco before I started my educational career, kindergarten, in Kinshasa, Zaire, which is right in the middle of Africa. We came back to the States, lived in West Texas and then East Texas, and then I wrapped up the first phase of my educational career at the International School of Bangkok. So I graduated from high school in Bangkok, Thailand, which is right smack in the middle of Southeastern Asia. And the reason why I'm telling you this is because I know what it feels like to be in a situation where I don't speak the native language. They don't understand what I'm saying often, and I don't understand what they're saying. And it didn't end with high school either, because after that I became a scientist. And so I'd like to tell you a really brief story here about when I was in grad school at the University of Illinois, Urbana-Champaign, working on my PhD in material science, and I had just gotten my second first author paper accepted to JACS. That's the flagship journal of the American Chemical Society. And I was very proud of this paper, so I called up my dad to tell him about it, and I said, "Dad, just got a paper accepted to JACS. It's on quantum dots." And he said, That's great, son. What's it about?" And so I told him the title of the paper. The title's here: Anisotropic strain-induced curvature in type 2 cadmium selenide, cadmium telluride, nanorod heterostructures. It's quite a mouthful. So after a bit of a pause on the phone, I asked him if he was still there. He said, "Why don't you send me a copy of the paper, and I'll try to make some sense of that title that you just read me." And that really gets at the heart of the message that I want to convey to you today, which is that the reason why so much great science goes untold is because there's a language barrier. We just speak the wrong language for the average person to understand. And I think it's more important now than ever for us to communicate science effectively, because we need to convince a very non-technical Congress that funding basic science is important. We need to convince the taxpayer that their money is being well spent. And we need to convince the next generation that a degree in science isn't just more homework, it's actually a lot more fun. And typically we're pretty good at giving fast-paced technical talks to an audience of our peers who probably understand what a type 2 nanocrystal heterojunction is. But we're not so great when it comes to explaining what we do and why it's important to our friends and family. And so to illustrate this concept, I'm going to tell you about what I do here at the lab, but first I'm going to do it not using layman's terms. And then I'm going to try again, but limiting my vocabulary to only common words. So I'm a postdoc here in Los Alamos National Laboratory in the chemistry division. I'm mentored by Jeffrey Petrega and Victor Klimov, and we work on quantum dots. So quantum dots are colloidal semiconductor nanocrystals that exhibit quantum confinement. Now this occurs when you make the crystals smaller than the Bohr radius, where you confine the electron hole wave function to smaller than their characteristic size. And so these are very, very small. So we can't see them with an optical microscope, much smaller than the wavelength of visible light. So we use a high-energy beam of electrons to create this electron microscope image. You can see individual quantum dots here. And when we do this, they exhibit broadband optical absorption, but relatively narrow, high quantum yield photoluminescence. And so I've got that absorption spectrum here. You can see on the left. It covers almost the entire visible spectrum, and then the photoluminescence for these particular samples are here in the red. So they would look quite red if you looked at them. And then I've got a couple samples here where I've added a type 1 heterojunction with zinc sulfide, which passivates the surface states. And is anyone still following me? Saw an eye glaze over right here, another eye glaze over here. And if your eyes did glaze over and you started looking at your cell phone, it's not your fault. It's my fault for putting you in the unfortunate situation of having to interpret what it is that I'm telling you. So I'm going to try that again, but this time I'm going to limit myself to using only the 1,000 most common words in the English language. So here's a hint. 1,000 is not one of the 1,000 most common words in the English language. This is why it's called 1,000 words, right? This is inspired by the webcomic XKCD, who made a comic using only 1,000 words, the most common 1,000 words in the English language, to explain the Saturn V rocket, which you can imagine is a pretty challenging thing to do. And it became very popular, and so it inspired many people, including myself, to try and do this with my own research. Okay, so what we do is we take important types of matter and we make it into really, really, really tiny pieces. When we do that, something crazy happens. When light comes in, the color can be changed to almost any other color. So in this case, purple is becoming orange, but we can change it to red or green just by changing size. So size sets the color. So how small are these? Well, I've got one right here to show you. Can you guys see it? In the back? Probably not. Of course not. I said these are really, really tiny pieces of matter. So if we took 100 of these and stacked them on top of each other and then did that 100 times again, it still wouldn't be as thick as a human hair. So we take these really tiny pieces of matter and put it into paint. These are actually liquids here. And then that allows us to make things that convert sunlight into energy for a lot less money. So how was that? Was that better? For those of you who actually understood the first part because you had the background, I'm guessing that you enjoyed the second part better, right? Because it's more natural. It's easier to follow what I was saying. And so I'd like to challenge each of you to go home tonight and try to write up a paragraph that explains what it is you do and why it's important, but limiting yourself only to the 1,000 most common words in the English language. And you can find the list on the internet, just Google it. In addition to limiting your vocabulary, I think another way to tell the story about what you're doing and why it's important is to focus on the applications, to demonstrate relevance. For example, iPhone is not one of the 1,000 most common words in the English language, but I'm pretty sure every single one of you knows the word iPhone, right? So I'd like to tell you a little bit about quantum dots and their application, about the applications of quantum dots now. And so they're used today in a number of consumer products for their display qualities. So the Kindle Fire HDX has a quantum dot display. Sony has a line of TVs that uses quantum dots. And the new iPhone is rumored to have a quantum dot display. It hasn't come out yet, so no one knows for sure, but Apple's filed a couple of patents relating to using quantum dots in displays. What quantum dots can do for displays is enhance the color purity, so make the colors more accurate and vibrant, but also improve the efficiency. So the battery life of the Kindle Fire tablet is one of the longest among the tablets that you can buy today. Here in Los Alamos, we're using quantum dots to make higher efficiency flexible solar cells of the next generation of solar cells. But people are also using quantum dots to make better medicines and improve medical diagnostics. Personally, I'm really excited about some of the lower tech applications as well. So for example, luminescent plastics. You can imagine a pair of sunglasses frames that glow bright green in the sun, or a stop sign that glows bright red in car headlights, or even fluorescent nail polish. In order to reach some of these kinds of applications, really all of these, you have to be able to make quantum dots inexpensively and non-toxic. And so that's one of our big focus areas here at the laboratory. And so as I've thought about what the next step in my career is going to be, I've decided to start a company. It's called Ubiquity, which is short for Ubiquitous Quantum Dots. Here's the logo. And in this endeavor, I've learned even more about the challenges of communicating science effectively because I have to convince investors that they should invest in my company. They're typically not PhDs. You have to come up with the quintessential elevator pitch, which is where you convince an investor in the time it takes to go up a few floors in an elevator that they should invest in your company. You know, you can't talk about quantum mechanics in 60 seconds, right? Even if you did talk, you had more time, you wouldn't do yourself any favors by talking about quantum mechanics when trying to pitch your company, under no circumstances. So I'd like to conclude by giving you a slightly modified, modernized quote from one of my favorite films, The Graduate. And this scene is from the very beginning of the film, where Ben, who's played by Dustin Hoffman, is at a party that his parents have thrown him to celebrate his graduation, and he's trying to figure out what he's going to do with his career, the next step for him. And the whole film's kind of about that. But in this scene, one of his parents' friends takes him aside to give him some career advice, and he's in the plastics industry, which is just beginning to blossom at this time. And he takes Ben aside and he says, "Ben, I've got just 2 words for you. Just 2 words. Are you listening? Quantum dots." There's a bright future for quantum dots ahead. What do you think about it? Good. It's a deal. Thank you.